Okay, it's November 20th, and we're going to finish the basics of statistics tonight, the basics of the Six Sigma, which is the statistical part. And then we'll jump into chapter 7. I think we'll have a little bit of time for that. So I want to say that the third homework is posted, and it's problems around calculating some control limits and some of that. So this is an assignment that you each have to do, but you can work on this together. So this is not something that you're going to have to. Okay. I hope that wasn't in response to my telling you that about the homework. Okay, so I'm trying to find Aaliyah here. Oh, you're Walker. I'm looking in the A's and you're in the W's because I have it sorted that way. Okay, so you're gonna do that homework. There's I think 4 questions. Some of them are multi-part, but it's about calculating these control limits and doing things like that. And so, like I say, you can work on it together if that makes sense. If you want to work on it with somebody else in the class, but you each have to turn in an assignment on that. So I hope that's clear with everybody. I will put that on the assignment itself. It's already in Canvas, but I'll take it out at break time or see if I can modify it and make sure that that is clear on the assignment. And then we still have the projects that are at the end of the semester. So this class goes fast with just the 8 weeks. So hi, Peter. Thanks for joining us.
Hi.
I was just saying that the next homework number 3 is an individual assignment, but you can work together on it if you need help, if you need somebody else showing you some of the statistics or anything like that. I'm going to walk through some of that in class tonight, and we'll see if it makes sense to you guys. And I will also be available throughout the holiday, probably after Thursday. If you need help, please reach out. Send me an email, but send me a text and tell me that you emailed me and you have a problem or a question or something like that. And I will either get back to you as quick as I will get back to you as quick as I can, and I will respond then if I can. If not, I will set something up in the next day or so, later that afternoon, depending on what time you text me. And don't feel bad if it's 10 or 11 o'clock at night. I don't care about getting a text that time of night. I probably won't say, well, yeah, I'll jump on the phone with you now and go through it. But don't worry about that kind of thing. And I'll help you get through it. Okay. So we'll take a look at those questions real quick at the as soon as we get through these slides, and see if you have an understanding of what to do and how to approach it. And hopefully these slides will help you do that. So I'm going to start. I think this is where we left off last time. We talked about these sample distributions and what we're trying to do. So we talked about the errors, the type 1 and the type 2, and we talked about these samples that we're taking and the distribution. So if you haven't had a lot of statistics, it's okay. I hope you've had enough math to know how to graph things and to look at them that way. So if you, the idea is that we have product that we're building. And so we're building those in lots, and we're taking samples from each lot to validate the quality in that lot and to make a decision whether or not we should go ahead and pass that lot and sell that lot, package it and sell it to our customers. So that's the basic scenario that we're looking at. So we want to say, all right, now we're going to take some lots of these parts, and they have to be the same type of part, not the same type of part, but really the exact same part that you're making. So if you're making a left hand, right hand kind of thing, then you have to have 2 separate part numbers, and you're handling the left hand over here and the right hand over here. And you're making it, you're doing 2 sets of control charts and everything. So everything is for one singular part number, one singular specification, one design. And then however you're making those. So we're looking at this, and we want to plot these in between from lot to lot. Sample number here, 1, 2, 3, 4. We're going to plot whatever that is, and then we're going to do these calculations. So we're looking at things that are variable data. So there's two kinds of data, variable and attribute. Variable is the kind that we measure. So we're measuring the length of something, the width of something, the weight of something, the diameter or circumference of something, thickness of something. But that's what we're measuring, something, some dimension or some number that we can actually measure and come up with a quantitative value for that. And we're measuring it in some detail. You know, we're not saying half a pound. We're saying like 0.48 pounds. So we're measuring these things in some detail. Let me see what's in the chat here. Oh, Latoya, welcome. I thought you were saying you couldn't hear, but like it's a different kind of hear. So good for you. Glad to see you. So we're going through what the rest of the Six Sigma basics, the statistics part tonight. So we're going to look at mean charts, and we're going to look at range charts, and we're going to look at how to calculate those. So we're going to, because we're monitoring the center of the process with the X bar charts. So we're looking at where those values are clustered around. If you go back and think about that normal curve, this is recording, right? I'm just looking for my little bar that says it's recording. So
yeah, it's recording.
Okay, I want to make sure. So if you look at that normal curve, remember we said the normal curve is centered around that the mean, that average. So that's what we're trying to do. The X bar is measuring how close we are to that average. It's helping us calculate that and then be close to that. So that's typically our target point. That's typically our design specification that tells us this is where we want to be. So then we're going to take some measurements of the parts that we actually build and see, are we getting close to that or not? So that's the X bar. And then the R chart measures the dispersion, which helps us define how wide and how tall that normal curve is. If it's wide and low, then that's a wide dispersion. If it's fairly narrow and tall, that's a close dispersion. And that's really what we want. We want a tight dispersion of these parts, which just means that statistically, all of those values are going to fall really close to the mean. So we're going to have more and more values that fall close to the mean versus that are around the mean, but they're scattered a little bit more, and it's the amount of variation. And then, so we're looking at variation and we're looking at the range. So that tells us the dispersion of that, the R charts. And so one is X bar and one is R. So now we're going to look at this and say, okay, here's the control limits. So don't let these formulas scare you, which they always do, because people look at them and say, oh my God, do I have to memorize that and whatever? So I would say on the exam, if you need to calculate this, and you will, I'll give you the formula, but you have to know what the formula means and what stands for what. So here's what we're looking at. We've got an X bar, double bar, and the X double bar means that it's the average of the average. If you remember back to basic algebra, where you took the average of something, you had X with a bar over the top, and they refer to that as X bar. So that's an average of the X's. Now we're going to take an average of the averages that we see, and that's going to give us X double bar. And then we're going to look at the number of samples, which is K, and then the mean, which is X sub I of the individual samples. So that just means that's one X bar. So don't let that be too confusing. We're going to have 10 different batches, and we're going to take a sample from each batch. So X sub 1 is from the first batch. X bar sub 1 is from the first batch. X bar sub 2 is from the next batch. X bar sub 3 is from the third batch. And what it's saying is we're going to add all those together and divide by K. So it's really just another average. We're going to take all of our samples. We're going to take the average of the sample, come up with a number, and then take all of those averages together and divide by the number of samples and come up with an average of the averages. So I hope that makes sense. And then we're going to take an R, a range, which is just the highest value minus the lowest value in each sample. We're going to get one value for that, the highest value minus the lowest. And we're going to add all those up and divide by the number of samples we have, that same number K. So it's where this looks kind of gnarly, it's really fairly simple math. So we use that to monitor the central tendency of the process. And then we're going to calculate the limits. We're going to calculate an upper control limit, and we're going to calculate a lower control limit. And to do that, we have to have that X bar number that we calculate. And then we're going to add in an A2, which is a control chart factor based on our sample size. And then we're going to multiply that times the average of the range. So we're going to say how far apart are these, and we're going to average that in. So A2 is going to be a given or something you look up from a chart. Then you take the average of the X double bars. You take the average of the X's, the sample is the X double bar value that you calculate, plus A2 times R bar, which is the average of the ranges. And when you add it to the X bar, it becomes the upper control limit. When you subtract it from the X bar, it becomes the lower control limit. And that's what we're trying to do, is to establish these control limits. So then when we do the range chart, we have a D factor, which is a control factor based on the sample size. And we have a D3 and a D4. So we use the D3 for the lower control limits and the D4 for the upper control limit. And we multiply that value that we pluck off the chart times the range, the average of the ranges, the R bar. So let me show you what that kind of looks like. So here's these factors for sigma control. So we're looking at how many observations we have in the sample size. So anywhere from 2 to 20. Then we have these factors. We have an A2 factor, a D3 factor, and a D4 factor. So D3 factors, if you remember what we just looked at, is the lower control limit. And in these cases, it says if we're only having small samples, then our lower control limit is going to be 0. And our upper control limit is going to be this number times the average of the ranges. So we'll look at one of those problems in just a minute. And then it looks like this. And I showed you this last week because, again, we're trying to see if we have this kind of wide and flat normal curve, or if we have a narrow, taller one that's a lot narrower in there. So, and then that's on our range chart. And then in the X chart, we're trying to see where does the average of our values, where is it going? Is it staying in the same area, or are we starting to drift one way or the other? In this case, we're drifting off, we're drifting up. So our dispersion is about the same. Our chart, our curve form is pretty much the same, but you can see that it's moving. So our averages are moving. And that's telling us that there's something going on with our average. It's not staying the same. So, it's good to have the curve stay the same. And so your range your control limit distance is about the same, but they're moving in a direction. In this case, they're moving higher. In this case, your control limits are okay, and you're staying really tight around the average, which is good, but you're getting more and more range in your sample size. So there's something going on that says your variation is starting to grow within that sample size. So that's what we're trying to ascertain. So we want to really look at this. There's a rule that says if you have a normal population and you take at least 30 samples, you'll have a very good representation of what that sample is in terms of acceptable or not acceptable. So, but we can't always take 30 samples, and we don't always want to take 30 samples. Now, taking 2 samples is often not enough, but sometimes if your whole population is like 5, it might be better just to measure all 5 units that you make rather than trying to take a sample of the 2. But it depends on what it is, how hard it is to take that sample, how difficult, and how quickly you need to process that through. So we're going to say that normally we like to take 20 to 25 samples. We calculate our statistics, we establish our control limits, and then we say, okay, do any of our parts, any of those points that we just plotted, fall outside of the control limits? And if they do, then we have an issue. If they don't, we say, great, we've got a process that's in control, everything's looking good, and we can pass this lot of parts because it's going to be good. If we find some that are out of control, some parts that are out of control, it says we got to go find what the issue is with this and see if we can figure out what went wrong to cause this one reading that's out of our control limits. And if so, then we want to resume the process, get another set of observations the next hour, the next day, the next shift, however we set it up, and keep plotting that data and keep looking at where we are in control. And then there's 2 other control charts that we can look at. There are a P chart and a C chart. The P chart is the proportion or the percentage of defects that we're looking at. And the C chart is the one we use to count, monitors the number or the count of defects per sample or per lot that we're doing. So we use the P chart when we are looking at things that are either pass or fail, good or bad. It turns on, it doesn't turn on. That's the kind of thing we look at. So a P chart is really good for a 2-dimensional assessment. Either it's good or it's bad. It passes or it fails. But when we have other kinds of things, then we want to use like a C chart. And the C chart says we're going to count things like scratches and chips and dents or cracks or breaks or bacteria, contaminants, or we're looking at calls that we get. So how many calls do we get? How many are complaints? How many are failures? How many of them are good job kinds of things? So we can use C charts for that. So with the P charts, we take the number of defectives we have divided by the number of observations. So again, we're looking for a P bar or the average P's. So again, we have 10 different sample sizes, 10 different lots that we're going to take a sample size from. Then we look at each of those lots and we say, okay, how many defectives do we have? How many defects are in that batch of parts that we made? And then we say, okay, we had 5 defects and that batch size is 200. So we take 5 divided by 200, and that's going to be our P bar, our average P. Then to calculate the standard deviation, we do a calculation that's P bar, average P, times 1 minus the P bar, and then divide that by how many observations we took, and take the square root of that, and that gives us the standard deviation. And you can do that in Excel. Excel will do that standard deviation for you. And then to calculate the upper control limits, we take the P bar and we add in a Z, which is another factor that we're given based on our sample size, and we multiply that times the standard deviation. And this gives us 1 standard deviation. So we add those together to be the upper control limit. We subtract the product of these 2 from the lower control limit, from the P bar to get the lower control limit. So stay with me, we'll do a sample of these. So when we look at the C chart, we take the C plus the same Z times the square root of the counts that we've taken, the square root of C, and we add C plus Z times the square root of C, or C minus Z times the square root of C. And I'm clicking on something that's not the right, that you can't see. So that's why I keep clicking the wrong place, because I'm clicking on the chart and not on what you can see here. So, you know, we have to think about, where do we use these control charts? And we talked a little bit about that last time. Where do we do the inspection? What kind of inspection are we going to do? How many samples are we going to take? How big are our lots, and how many samples are we going to take? How often are we going to take that sample? Are we going to take it like every hour, every shift, which might be like within an 8-hour time frame, every day, every day? Excuse me, I'm going to sneeze here. Excuse me. Or even like once a week. Usually you have enough values that you're taking it maybe once an hour, once every 4 hours, once every shift, or something like that. If you don't have enough values that you're taking it once a week, you've really got a lot of time and a lot of other variability that can come into your process. So how frequently are we going to take the samples? And then are we going to use this in terms of attribute data? Are we taking samples of something that we measure? Or are we counting these things, or looking at go and no go, pass and fail type things? So we're going to look at that. Let's hold off on that. Let me stop this and let me show you an example. Let me just pause this. So I did not record any of that I just did in the examples, which makes me very unhappy. Well, for those of you who are here and saw that live, hopefully you can remember that. And when I post that chart, then that will help you. I forgot, I thought I was being clever by pausing it while I was looking for that file, because I couldn't find it. I'd shut it down earlier and I'd forgotten that I'd shut it down. And then when I went to pick it out, I remembered it. So if you need help, like I say, reach out for that. Let's see what else we have. So then we have run tests. The run test is, we're looking for patterns in a sequence. And so we're looking at that over time. So this will tell you, you've got a run test. So the reason we plot things and we get a visual graph of it is because we want to be able to look and assess different things. So we're looking for this sequence or some kind of pattern within the chart. So, and you can see in each of these, we're still staying within the upper and the lower control limits over time. So again, there's time down here, numbers of samples that are growing. So if in this case, we see that we started out down here, now we're going up and to the right. So we have a trend, right? We're headed in that direction. And it tells us, if we don't look at this process, then what's going to happen is pretty soon we're going to be up in here, right? Does that make sense? I should do it over here, right? We're going to be up in this area, because this line, if I project it out, is just going to keep jagged going this way, right? Isn't that what you would assume? This, we see an up and down kind of thing. So we started here pretty close to the middle. We went down, we kind of bottomed out. Now we went up, we went down, we went up, we went down. So you would expect this to go kind of up again, right? And then back down. So we're not going too far up. We're not going too far down, which is good. We would want to watch that. But we would want to say, why are we having this cycle, this wave pattern of up and down? It might be due to a tool that we're using, or an operator, or something like that. But it would be probably worth investigating to say, what is this? What's going on here? Unless this was something that you were trying to do. So if you were trying to get values that went from low to high and back down, then that might be pretty good. but I'm guessing that it's probably not intentional. You would want to see it a little more flat. In this case, the bias, what you're seeing is you're seeing a lot of up and down, but you're seeing a lot of things below the line, way more below the line than above the line. And what this is probably telling you is need to recalculate your control limits, and you're probably going to see them shift downward, which may not be what you want to have happen, because it's kind of going toward a trend where you might end up being down below where you want to be. So in this case, it's probably worth recalculating those limits and to see what's going on, and find out why you have so many values that are under the average. Because if you took an average of this, because you guys have done enough math to know this, if you took an average of this, the average probably isn't going to be this high, right? Because I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I probably have 20 or 25 data points here, and I only have 1, 2, 3, 4 above this dotted line, which is supposed to be the average, and they aren't really spiking up. So 4 data points, 4 values over the average probably is going to mean you have a lower average, right? If you recalculated the average for this, it's probably going to be lower, and therefore it's going to lower your control limits. So again, these are tools to help you manage the business. They are not absolutes. They are not telling you exactly what to do, but it's giving you warning signals, or it's giving you validation that what you're doing is working, and you should continue to work with those process parameters, those process constraints or boundaries that you have, because either it's working or it's not. In this case, this bias, it tells you there's probably something going wrong here, going south. Oops. And then too much dispersion means, am I going the wrong way? Yeah. This one says I'm getting wider and wider. This one makes sense from an average perspective, right? This average looks about right. And if you're just going to eyeball where the average is, it says, yeah, I've got about as many data points above that line as I do below. But they are getting pretty wide. Now, here they were pretty tight. Here they're a little bit tight, but we've got this big swings here from high to low, high to right on the average, to low to up here, up, down, down again. So this just says I'm getting a lot of variation in there. The dispersion is getting pretty wide. So I might want to go look at my process and say, what's happening here? And how do I get that a little tighter? Because that might not stay a process that's giving me good parts. If I let this continue to go, these might get wider and wider, and I'll start getting more data points outside of the control limits. So again, none of the books and none of these examples are really good about showing you, hey, how does this look in relation to the specification limits? Because if I had specification limits that were way higher than this, I might say, I don't really have to worry about it, because I've got growing dispersion here, but I'm still not using most of my specification tolerance. On the other hand, if your specification limits are just above and just below these control limits, then you might say, I'm very close to having a problem, and I need to go evaluate that process and see what's happening there to see if I can fix it. So one of the things that we say is, is the process capable? So once we've determined that it's stable, which is staying within those control limits, then we're saying, is it capable of producing that output in an acceptable range on a continuing basis? So we're looking at, again, the specifications which are given to us by engineering, which say this is the parameters for the part. If it doesn't meet this, it's not going to work in our finished good, whatever our finished good is. So is that process variability? Is it natural? Is it just in the process that we maybe get those little waves or something? Or is it something else going on? Is it external forces that are working? Or is it the process isn't working. So that process capability tells us the variability of the process by looking at the process width relative to the variation that we have from the specification. So that's kind of a convoluted and confusing way to say, are we close to or are we far away from our specification limits? So we can have a process that is like this. So here's our process variability. Here's our lower specification. Here's our upper specification. Sorry about that. And I'm drawing again on the wrong. I'm drawing again on the wrong screen that I have. So here's my lower specification. Here's my upper specification. If this is my normal distribution of values, it's telling me that I really am not in pretty good shape, because my normal distribution says I'm going to have quite a few values here, and those are going to be outside of my specification. So again, my control charts can look really good, but my specification isn't. So I'm not meeting that specification. So I need to go tweak my process and get a better process that's tighter in. Or I can have one that looks like this. So if here's my specification, my lower specification, here's my upper specification, and my control chart says my values are going to fall like this, it says I'm going to be okay, but I am on the line. So I'm using every bit of that tolerance given to me in the specification that I have. So we've got however wide my specification tolerance is, I've got a target value plus or minus something, but it says I'm using all of that is there. And that might be okay. And it might say, can I get that tighter? Because it's really could be a problem if I get any kind of a little change, excuse me, or tweak that throws me out, then I could end up looking more like this chart here, which is going to tell me you're going to have problems because your process really isn't in control, isn't really capable of meeting the specification limits. This says you're right on the hairy edge. Your process is capable of meeting the specifications, but barely. Now, if I have this kind of a chart where my lower and my upper specification are well outside of my control limits, and this doesn't draw control limits, but your control limits are going to be like here and here. So that says, then I'm going to have, I'm going to be okay. So I'm going to have a more capable process because I am going to be able to stay within that lower and upper specification on a continuing basis without sweating a lot. It doesn't mean I can take my eye off and never look at that process again, but it says I'm probably okay to keep monitoring it. Maybe I can take fewer samples or samples less often. So before I said we're taking like 10 in the morning, 10 at night. Maybe it says, let's just take 10 during the day because our process is looking very capable. So I don't have to take as big a sample as often as I have been. So those are some of the things where you can save money by doing that. Once your process gets in control and gets capable, then you say, okay, it doesn't mean you never have to check it again, because that would be foolish, right? Murphy is alive and well and hits all kinds of us in all kinds of places all the time. But it says I can probably check less often or I can check fewer samples of a lot. Maybe I can put two lots together and check the same kind of sample size. So I'm not checking as frequently. So I can save a little money on my inspection and still feel confident that the parts I'm producing through this process are good and are going to give me the result that I anticipate and that I need in order to satisfy my customers. So we have what we call a CP and a CPK. So we use these, the tolerance limits on this to calculate that. So we have the upper tolerance limit and a lower tolerance limit, and we calculate that by taking the difference in the specification limits. So it's like the range, we take the high number minus the low number. And then we divide that by 6 times 6 sigma of the process that we're measuring. So when we look at that 6 sigma, it's a total of +3 and -3 standard deviations. Remember those charts I showed you at the first last week that had like the 68%, the 97%, 99%? Those are what we're looking at. So we calculate the standard deviation of the process, and then we'd say, okay, we're going to take the upper tolerance limit minus the lower tolerance limit, specification limits. I don't know why they use T's here and SL's other places, but they do. And then divide that by 6 sigma. And if that gives us a number that's pretty high, then that's a good thing. So we're looking for CPs, and we're going to talk about CPKs here in just a second. We're looking for those to be 1.0 or higher. If we have a lower number than that, it's not good. Even a 1.0 number for it gives us about this. It says, yeah, we're okay, but we can't mess up very much. So we'd like to be 2.0 or higher in this area. So there's the CP, and then this is the CPK. And the CP and the CPK do not stand for anything. They're capability indexes. So they're not, it's not an acronym. I get asked that almost every time I teach this. What does that stand for? And it doesn't stand for anything. So then the CPK is the minimum of the tolerance or the specification limit minus X bar divided by 3 sigma. And so you either take the upper tolerance limit minus the X bar, or X bar minus the lower tolerance limit divided by 3, that, and you look at the minimum of that. And the lower value there tells you what your CPK is. So this I don't think I gave you any homework on those. And that, what I would put on the test about the capability index, the CP or the CPK, is that it is measuring the amount of the tolerance that you're using in the specification that's given. So it's the capability of that, and that you want a higher number, definitely higher than 1 and higher than 2 is really good. So to improve the process capability, we can expand the tolerance limits. It doesn't say that here, but we could. We can simplify, we can standardize, we can do the mistake proofing that we talked about before, the poke-yoke. We can upgrade our equipment, we can automate, we can kind of lean it out in order to get that higher capability so that we make some process improvements in there. The capability measure itself, it's not necessarily stable, and your process output may not have a normal distribution. And if it doesn't, well, then this changes a lot of things. And then your process may not be centered, but you're still using the capability calculation. And so you might not get the kind of answer that you really want to get. But at the end of the day, quality is the primary consideration for all customers. You know, we all want a certain level of quality in what we buy. When we're making things in the factory, we want a certain level of quality to be able to sell to our customers, because we should know what our customers are expecting. And that way we're going to satisfy them, and they're going to come back and buy more stuff from us. So it's important that we understand these strategic levels of quality and these strategic principles of quality, and make sure that our product and service design are such that we can have and create and implement capable processes so that they are in control, can make things repeatedly for our customers. Now, if we're making, you know, if we're hand making quilts or, you know, clothing or one-of-a-kind items, then this is not what we're really looking for. And this is not how you measure quality of something that you only make 1 of or 3 or 4 of over the course of a year. I was looking at something today, something on the internet, and it had like, I don't know, like the wedding dresses of the British or something like that. And all of these are these most expensive wedding dresses or something. I didn't look at the article. I just saw the headline. And, these are very expensive, one of a kind items. You do not put quality measures of this kind on that type of output. If you're handcrafting a coffee table for your living room, for your parents or whatever, you don't put this kind of quality measurements, quality approach. These are for things that are done repeatedly and in at least small quantities, so that you can actually track and see, am I consistent in this? If you're trying to make things that are one of a kind, that are unique, that are unicorns, this is not what you want to do, because you don't want them to be consistent or repetitive. But if you are making things that are repetitive for your customers, which I'll say most of the businesses are doing, whether you're making sandwiches or cookies or iPhones or computers or toaster ovens or, 100 different things, you're really looking at how can I measure this? How can I assess my quality? Not just is it good, but do I have a way to perform this that is good, that is consistent, that is going to let me do this over and over and over? And you can apply these things to some services if you have, again, the quantity that you're looking for, like customer service or ticket issuing or things like that. It gets a little more complicated and you have to give some more thought to what you can actually measure, but you can do some statistical analysis around that. So again, lean is a big portion of this kind of quality approach. And then the statistical piece is also an important piece when you have the numbers and the repetition and the requirements for getting your quality that good. So that's why we do that. So that's the last slide I have here. So I am going to stop this. What time is it? It's 8:09. So I'll stop this recording, stop the sharing, stop the recording. And I can't believe I did that example without recording it. That makes me very, very unhappy.
So can I ask one quick follow-up?
You can.
So just to reiterate or try to sum up what you said to make sure I understood it correctly. Essentially, if you're in a business that is making a more unique product or solving more unique problems, then lean is your probably solution source more often than not. And then if you're making a product that is meant to be repeatable and of consistent quality, that is not meant to be unique, then that would be where you also can layer in Six Sigma controls on top.
Right. Lean approach will help any process. Whether it's a set of forms you need to fill out or have people do things, or the DMV that's getting customers in all the time, you can look at ways to lean that out. But you want to, if you get a little more sophisticated and mature in your quality measurement, your quality systems, then you can, and I think you said layer in, I think that was a good way to say it. You can bring in the statistical controls that can help even more. And definitely on manufacturing processes where you're doing the same things over and over and over. Anything that's repetitive, you can apply those to pretty readily. Very well put, Ivana.
What about if you have semi-repetitive stuff, like event planning, let's say?
Okay, so tell me something that's repetitive about event planning.
You probably have similar vendor needs on any event, or contract needs, or that kind of, or most events you'll have to think about bathroom needs, or that kind of stuff.
Okay, so you could use so bathrooms, like porta potties, you could use some statistics to figure out how many of those you need for so many people. because you want to say, how long you can measure the length of a line, how many people are in line at any given time. And you can plot that out and you can say, okay, what does this tell me about that? Like, an hour after the thing opens and every hour that it's open, how many people are in line for the bathrooms. And then you could say, okay, if there's no more than 4 or 5, that's probably okay. And if it starts getting long, it says I probably need more. So for the size of the event, or how they're spaced out, or things like that. How many chairs and seats you need, or tents, that kind of thing, for how many people are going to be there. Now, some of that with event planning is a roll of the dice, right? You say we're planning this fair and we expect 300 people. Well, if only 100 show up, that's going to give you something else. And if there's 600 that show up, that's going to be a different dynamic, right? But you can do some statistics around that. So what can be measured? What's going to give you some information? What's valuable to measure? It's really hard sometimes. You say, oh, we can measure this. All right, if you can measure that, does that tell me anything? And is that measurement going to help me make decisions or help me assess whether I'm doing the right things or not? So you have to kind of think that through. And then, you think it through from both sides. What can I measure? And then you want to say, okay, what do I want to know? And then in order to get that information, what can I measure to get that information? And sometimes they don't match up very well. Then you look for correlation, like maybe how many people are there versus this. And so you're trying to pull things in, because I've gone into a factory, and this is a factory, which is a different thing, but they have beautiful charts and all the charts look like everything is good. And then I look at the parts that they're sending me and they're crap. So I'm like, how can you have really good charts and my parts don't work? It's because they're not tracking the things that make my parts work or not work. They're tracking something that's going to make their chart look good, not what's really telling me about are my parts going to work when I plug it into my whatever I'm making that I'm buying from them. I'm buying something from them, like a fan, to plug into my computer. And if it says their fan is really good, but it doesn't work in my system because what they're checking is not what I'm checking. So then you got to go back and say, okay, what else can you check? What can you do differently? So, some of the things you have to say, I can't measure. So, all right, are there things that I can count? Are there, rejects, complaints? Are there different things that I can do to do that? Does that help?
It does. Thank you.
Okay. Any other questions? I'm going to go ahead and stop the recording.